Last episode, we made a model faster at reading. Now we go after the harder, slower half, the writing. And here's the frustrating truth about how a language model generates text. It does it one token at a time, in a strict sequence. It produces a word, feeds that word back into itself, runs the entire model again to produce the next word, feeds that back in, and runs the whole thing again. To write 100 words, it runs the full model 100 separate times, each one waiting on the last. That sequential bottleneck is why even a fast model streams its answer to you word by word instead of all at once. Speculative decoding is a genuinely clever way around it, and the most beautiful part is its promise. It makes generation faster while changing the output not one bit. Quick note before we dig in. If you find this useful, subscribe and drop a topic you want explained in the comments. Now, let us get into it. Here is the whole idea in one sentence. Speculative decoding speeds up generation by having a small, fast draft model guess the next several tokens, and then having the big, expensive target model check all of those guesses in a single pass, keeping the ones it would have written anyway and throwing away the rest. To see why that is even possible, you have to remember something we learned back in the quantization and VRAM episodes. Why is generating one token so slow? It is not mainly the math. Back in episodes 8 and 9, we saw that inference is memory bandwidth bound, meaning the real bottleneck is the time spent hauling all of the model's weights out of memory and onto the chip. And here is the key insight the whole trick rests on. To produce one token, the model has to stream all of its weights through once. But it turns out that if you hand the model several candidate tokens at once, it can check all of them in essentially that same single streaming pass, for almost the same cost as checking one. Verifying 5 guesses is nearly free compared to generating 5 tokens the normal way. The slow part was never the checking, it was doing it one at a time. So here's the loop. You pair the big target model with a small cheap draft model, one that is much faster but less reliable. The draft model quickly races ahead and proposes, say, the next 5 tokens. Then the big model takes all 5 and verifies them in one pass, asking, for each position, would I have produced the same token here? It accepts every guess from the start that matches what it would have said, and the moment it hits one that does not match, it stops, discards the rest, and supplies the correct token itself. When the little model guesses well, you just got 5 tokens for the price of roughly 1. When it guesses badly, you fall back to normal speed, but you are never worse off. In practice, this commonly buys a 2 to 4 times speed up on real workloads. Now the promise I keep repeating because it is the whole reason this technique is special. The output is provably identical to what the big model would have produced on its own. Not similar, not close, identical, because the big model has the final say on every token and only ever accepts a guess that exactly matches its own choice. Contrast that sharply with quantization from episode 8, where you traded a little quality for speed and memory. Speculative decoding trades nothing. There is no quality cost, no subtle degradation, no catch. It is pure, lossless speed. That is rare and worth pausing on. Let me name the real methods because this is a live and fast-moving field. The classic approach uses a separate small draft model, but the leading modern techniques are cleverer. eGLU, now in its 3rd version, eGLU 3, has become something of an industrial standard, drafting from the target model's own internal features and using a little tree of candidate guesses to push its acceptance rate high. Medusa takes a simpler route, bolting a few extra prediction heads directly onto the big model so it can guess several future tokens by itself, no separate draft model needed. And the lightest trick of all, n-gram or prompt-lookup decoding, needs no extra model at all. It just guesses that text is about to repeat by copying likely spans straight from your prompt, which works shockingly well for tasks like summarizing or editing a document. And all of this ships in the real inference engines you would actually use: vLLM, SGLang, TensorRT-LLM, and llama.cpp for local runs. So how does this land depending on who you are? As an individual running a model on your own machine, this is a direct win. Tools like llama.cpp can use prompt lookup and draft models to make local generation noticeably snappier on the same hardware, with the exact same output. As a startup serving a model to users, speculative decoding is often the single highest return optimization for response speed, faster answers, and lower serving cost, with no quality trade-off to explain to anyone. And as a large enterprise running inference at scale, this is core serving infrastructure, where a 2 to 4 times throughput gain on the same GPUs translates directly into serving more users for the same money, which is why every major inference stack now supports it. So let us bring it home. Generation is slow because a model writes one token at a time, and each token means streaming the whole model through memory again. Speculative decoding breaks that by letting a small draft model guess several tokens ahead and having the big model verify them all in a single pass, keeping only the guesses it would have made itself. So you get a 2 to 4 times speedup with output that is provably identical, using methods like EAGL3, Medusa, and prompt-lookup across engines like vLLM and TensorRT-LLM. We have now made the model cheaper to hold, cheaper to read, and faster to write. There is one last idea in this bonus track, and it is the most ambitious of all. Instead of speeding up a giant model, what if you could take everything it knows and pour it into a small one? A little model that learned to think like the big one. That is model distillation, the finale of the whole course, and it is where we go next. Content, that is the core of it. If this helped, hit like and subscribe, ring the bell for the next deep dive, and tell me in the comments what you want broken down next. Thanks for watching.